Morning, students. This is Gaurav Saxena, and I am going to tell you about basic principle of ledger. We have already done some of the work in the classes, but due to this lockdown, so let us restart with the basic principle of ledger. And I hope you will get the benefit of this revision. And in the next lecture, I will definitely give you the more details about ledgers and other topics of this unit. So what we have discussed was the principle of ledger, and I think we have discussed it about the absorption, spontaneous emission, and stimulated emissions also. So let us quickly revise it that the basic principle for any of the light is that definitely some of the electrons should move to the higher levels. You can see in this diagram that there are some of the levels which are called ground state, metastable states, singlet states. So usually we have the infinite lifetime for all the atoms which are in the ground state. There are some states which are metastable states and which are going to be used for this laser perspective. So I will discuss detail about this metastability. There are some of the singlet states also. So these states have their very small lifetime. Specifically, singlet states have 10 to power minus 6 second or minus 7 second or minus 9 seconds. So that's why. So the electron lies there for a very small time interval and then they return back, the atoms return back to the ground state. This delta E is the change is the energy. So if we want to excite, we want to send the atoms to the singlet state or metastable state, then we have to provide the energy to the system. So this was the absorption. The left side is a diagram of the absorption. So in this absorption, you can see that there is a lower level, the atom is there. So once we provide the photon, that photon should contain energy. That should be the difference between these two levels, E2 and E1, that is E2 minus E1. And then the electron will move from ground state to the upper level or the excited states. So this process is known as this absorption. Moreover, once this electron will reach here, then this electron can survive up to 10 power minus 9 second only and it will return back to the ground state. This process by which electron return to the ground state, then it will emit some of the energy, which is again the difference between these two levels, and that energy will be liberated in form of photons. And this kind of emission process is completely random. This kind of emission is actually called spontaneous emission. And to remind you that this is very random phenomena, and that is why the photons which come through this process are actually incoherent. There is one another process which may be used in this laser principle, and that is the stimulated emission. In fact, the full form of the laser is light amplification by stimulated emission of radiation. So, sorry. So this stimulated emission is that we force this particular electron to return back to the ground state. This is by we stimulate this particular photon electron to return back to the ground state. So for this also we give some of the photon there, and that photon stimulate this particular electron to return back to the ground state. In the consequently, we have the two photons now. One photon which come here and which only stimulate here. The second one is the energy difference which is from these two levels. Now these two photons are very important. These two photons are exactly of the same energy, same frequency, and same phase, and that leads to these two photons as a perfectly coherent photon. So this kind of emission is referred as stimulated emission when we stimulate the whole process, and from this process we got the photons which are actually completely coherent photon. This is the first requirement for any of the laser action. The light should be coherent, and the coherence, if we want to get the light, coherent light, perfect coherent light, so the only thing which we have to deal with the stimulated emission. In a very nutshell, I have just shown this before emission, during emission. This is what happened there for stimulation. After emission, we will got the atoms, the photons, which are perfectly in that coherent mode. To get the laser beam, we required this thing. Number one thing, we required population inversion. Population inversion means because the laser light is a very high intense light. To get the high intensity, we require more number of photons. To get the more number of photons, we require the number of atoms which should be more than, which should be in the excited state or in metastable state. Their number should be more than what we have in the ground state sometimes. So it is also referred as N2 if the number is there N1 is the number in the ground state, then the essential condition for laser is that N2 should be greater than N1. So this process by which we can populate this excited state or metastable state, this process is known as population inversion. And once the population inversion is achieved, then this stimulated emission can reinforce all the electron or the atoms to return to the ground state, and we have a variety of number of all the photons, and these all the photons are once again coherent and produce the laser light of high intensity. To get the example of laser, we have shown this helium neon laser. So the helium neon laser is that we have this kind of a tube in which the helium and neon gases are actually in the mixed stage, and this mixture is 10 to power 1. I will tell you why this 10 to power 1 is there. We have the fully silvered mirror here by which the any of the photon coming here can reflect it back completely, and there is partially silver mirror also, so which may reflect it or which may transmit the light also. We have the electric discharge here, so we produce the pumping. Actually the pumping is electric pumping here in helium neon laser, by which the helium atoms get excited. So the basic principle is that we provide the pumping, electric pumping. By electric pumping, this helium atoms get excited, and once helium atom get excited, then it will excite the next neon atoms. So ultimately helium is playing a role of an agent by which the neon atom get excited. So we plan to excite the neon atom. Basically, neon atom will provide you the whole laser light. Let us see in this energy level diagram. In the helium atom, you can just see this helium atom is excited states. They all are excited, and these two states are actually metastable state, which is the requirement, because metastable states are having the lifetime which is more than the lifetime of an excited state. And importantly, if metastable states having 1,000 times more the time more than the excited state, then it will give to the population in the more, and the more atoms can survive in this metastable state. So for the helium, actually they are the metastable state. However, our basic aim is to excite neon atom. So ultimately, these two states are very, very in line with the neon atom's excited state or the metastable state. So helium atom collides with the neon, and then neon get excited in this way. Now, neon is excited. These states are already metastable state. So population inversion has been achieved there in 3s2 and 2s2 states. You can see. Now there are three chances. Number one chance is this: if suppose the transition take place, but this transition, number one, number two is that this transition will take place, and number three is that this transition. By these three transition, these all the metastable state can produce the photons there. However, this particular nanometer 339 nanometer is not our use, because this is not in the visible region. Similarly, this particular one, which is again 1152.3 nanometer, is again not in the visible range. I hope you remember the visible range is 400 nanometer to 600 around nanometer, 700 in fact sometimes. So look at this stage. This particular one is that where we have this transition from 3s2 to 2p4. This transition will give you 332 nanometer laser, and we reinforce this transition there. This is where the stimulated emission take place, and by this stimulated emission we will get the laser light, which is of 6328 angstrom or 632.8 nanometer. After this, all the photons, all the electrons will return to this state 2p4, and after this, by spontaneous emission, they will reach to here, and then from this state, after the collision of the walls, they all the atoms reaches to the ground state. In this manner, and in this by this energy level diagram, one can study that how the energy levels play a crucial role in deciding the laser in the helium neon laser. So in terms of application of laser, I have discussed it already in the class, but there are some of the specific applications of the laser. One of the welding and cutting. Nowadays is a variety of the welding and cutting are done using this carbon dioxide lasers there. In communication, we are using the variety of communication signals there. Optical fibers are used there, and in which we are having the internet facility, which is long distance internet facility. This is also being done by laser. Barcode scanner, we are all familiar with barcode scanner. Laser printing is nowadays changed all the era of the printing. CDs and optical devices, readers we use here. Surveying and ranging, to the variety of the range, we use the fast laser pulses. Then laser cooling is also important. Nowadays, the low temperature devices are manufactured by laser cooling. Laser spectroscopy is now in the use in a fundamental significance or understanding for the basic atomic process. And the important one is the holography also. Nowadays, the holography is replacing photography, where you can feel the whole three-dimensional image or whole three-dimensional object right in front of your eye by simply the superposition of laser light. For the next class, I will discuss the superconducting laser and some of other applications of lasers and its principle also. Thank you very much.